This is Unit 10, Lesson 2, and today we're going to talk about exponential growth and decay. This is just going to be an introduction to growth and decay. We're going to do more with it later in the chapter. For now, the main thing you need to understand is that if you have an exponential function, it will be in the form y equals a times b to the x. The number here, your b, is going to be the only thing to the power. What do those things represent? Well, your a is going to be your initial value or your y-intercept, your initial population. So if they give us an exponential growth and decay problem and say the original population of a town is 100 people, then your y-intercept would be that 100 people, or 0, 100. B is going to be the rate of change or the rate of growth or decay. So B determines whether it's a growth or a decay problem. It will be a growth problem if B is greater than 1. Now usually it's 1 point something. It can be bigger than that, but most of the time you're not going to have a growth that's too much bigger than 1. For a decay problem is when you have B between 0 and 1. It's a decay problem when the population is decreasing over time. It will be a growth problem when your population is increasing over time. And in this section, we're going to be talking about what is the rate of growth or what is the rate of decay. We're going to be talking about how to write an equation when we're given two ordered pairs. We're going to talk about identifying whether it's growth or decay. If you look at this equation right here, y equals 1/2 to the x power. Well, if you think about it being in the ab to the x form, isn't your a going to be 1? That's understood to have a 1 in front. So my y-intercept would be 1. This 1/2 is between 0 and 1. So this is a decay problem. Looking at this one, 3 times 2 to the x, my y-intercept would be 3. This is a growth problem because your b value is greater than 1. Here's another one. It's written a little differently. F of t equals 2500 times 1.052 to the t power. Here we have t and f of t. So instead of using x and y, they're using t and f of t. T is understood to be your x variable, your independent variable, and f of t, your y value. And so here the a is 2500 and the 1.052 determines growth or decay, and in this case it will be growth because it's greater than 1. In these examples, the directions are given the ordered pairs. Find the growth or decay equation. Now, we learned in the last segment that your growth decay equation is y equals a times b to the x. So if we plug these ordered pairs in to the formula, we will be able to find the equation of the exponential function. So one thing we learned is that your a value in the equation is your y-intercept. So if they give you the y-intercept, it's going to make it very simple. We see here 0, 2 would be the y-intercept, the place where it crosses the y-axis. So I am allowed to just understand that a is 2 here. So if I plug that in, I have y equals 2 times b to the x. Then I can plug this ordered pair in for my x and y to figure out what b is. So y is 6.75. We've got 2 times b, x would be 3. So the next thing I'm going to do is divide both sides by 2. 6.75 divided by 2 is going to be 3.375. That equals b cubed. And then to figure out what b is, I would take the cube root of both sides. And again, I can do that in my calculator. So I'm going to take the cube root of 3.375 in my calculator. I could use Desmos as well. When I do that, I get b equals 1.5. So my exponential equation here would be y equals, I'll just put the answer right here, y equals 2 times 1.5 to the x power. This one is not quite as easy because it didn't give us the y-intercept. So what we're going to have to do is we're going to have to take our formula, y equals ab to the x, And in that formula, I'm going to plug both of these ordered pairs. So for the first one, I would have 4 equals A times B to the second. And for the other one, I would have 32 equals A times B to the fifth. And then if I think about that, I could do substitution, use substitution to solve it. So I'm going to look, I think this one's a little bit easier because the numbers are a little bit smaller. So I'm going to get A by itself here. If I do that, I would have 4 over B squared is equal to A. Then I could take what A equals and plug it in over here. So 32 equals 4 over B squared, I replace A with what it equals, times B to the fifth. Now, if I do that, I end up with 32 equals 4B cubed, because the B to the fifth and the B squared cancel. If I divide by 4, I have 8 equals B cubed. And then if I take the cube root of both sides, I end up with 2 equals B. So my B value is 2. And then to solve this one, or to write the equation for this one, I would need to then find A. So B is 2. So 2 goes in for B. So I've got 4 over B squared is 2 squared, or 4, equals A. So I know A is equal to 1. And so my equation would be y equals 1 times 2 to the x. You could put the 1 here since you know that that's what A is. It would not be necessary to put the 1. You could have y equals 2 to the x as well. But we've written the exponential equation here. Another thing I want to talk to you about is, what do exponential equations look like when we graph them? And you're going to see that exponential equations get very large or very small quickly. They will grow exponentially, or they will decay exponentially. They get big or small very fast. And so I'm going to show you in the next segment what some of those look like. And then we're going to talk about how to determine the percent of growth or decay. So the next thing I want to do is show you something on Desmos. They may ask you what a graph looks like when it's graphed in Desmos, or they might ask you to predict what's happening with a graph. Is it going up or down? Is it an exponential function? And if it's an exponential function, it will have a specific shape, a very specific shape. It will be going up or down very, very quickly. And it will shoot up toward positive infinity or shoot down toward negative infinity very quickly. And so you need to see what that looks like. Now, later in the chapter, we will compare exponential functions and logarithmic functions so that you can see that the two types of functions are inverses. But for now, we're just going to look at what a normal exponential function looks like. Now, I'm going to add some sliders in here. I'm going to add an A and B slider. And the only reason I'm doing this is so that I can show you what happens as A changes and as B changes. I'm going to move B, and I'm going to make it 2. Okay, so B is 2. And here I'm going to leave A as 1. So if you think about what that would look like, that would be the function y equals 1, A is 1, times 2 to the x. Okay, normally I have that x on the outside of the parentheses. It really doesn't matter because it only pertains to the b. So if it's on the inside, it really doesn't matter. That's fine. What we need to notice here is A is 1. Didn't we say that was our y-intercept? Well, does that hold true? Is that where that crosses the y-axis? And yes, it is. Okay, I'm going to leave B 2. I'm going to increase A. Let's make A 5. So now A is 5. Is A, or the y-intercept, 5 in that case? Yes, it is. And you see, as A gets larger and larger, this thing goes up toward infinity more quickly. As A goes down in size, and I'll keep it positive here at first, it's going up not quite as quickly. See, this steepness doesn't happen until we get over toward the right a little bit further. But the larger our A value, the quicker this thing shoots up. Okay? So that's something you need to know about A. I'm going to put A back at 1, just so we can see what happens if B changes. So as B gets larger, look at what happens.
my y-intercept is still at 1, it's still at A, but it's going up quickly. See how that happens? It goes up more quickly than if B is smaller. Okay, now let's consider, I'm going to put B back at 2. Okay, let's consider what happens when A is negative. If we move A to a negative number, now at 0, it's a straight line. Well, that makes sense, doesn't it? Wouldn't that be y equals 0? Because if A is 0, this whole function is 0. So it's not going to be exponential at all. It's just a horizontal line. But if we make A negative, look what happens. The smaller the negative number, the steeper that decline is, the quicker that decline is. Okay? So that's what happens when A is negative. I'm going to put A back at 1. What happens when B is negative? All right, here's B is 1. Well, doesn't that make sense? If B is 1, then we would have y equals whatever A is. Y equals 1. That's a horizontal line. See how that works? What happens when B is a decimal? Something between 0 and 1. Look at that. It shoots up toward the left. Goes in the opposite direction. Okay? So now, what happens when B is negative? Well, at B equals 0, look what happens to the function. What happens when it's negative? It's gone. It's not possible for B to be a negative number. It's not going to work for our exponential functions. Okay? And you can look on this graph and see it is nowhere to be found. So B has to be positive. All right, what happens if A is negative and B is, I'll just say it's 1? Well, if B is 1, isn't this just going to be 1? Because no matter what power x is, this is just going to be 1. So we'd have y equals A. Whatever A is what my horizontal line would be. So B is going to have to be something other than 1. If it's larger than 1, look, it's going down. A is negative. B is larger than 1. It goes down. What happens if B is between 0 and 1? There's 1. There's between 0 and 1. Doesn't it go in the opposite direction? Everybody see how that's working? Okay, so that just gives you some ideas of what your exponential functions are.
In this section, we're going to be finding the percent of increase or decrease of the given exponential equation. And here they tell you that f of t is equal to 2500 times 1.052 to the t. And they tell you that that represents the change in population over t years. Now, if they ask me what the initial population of this was, I would know that the initial population is this a value, 2500. And what they're asking me here is to figure out the percent of increase or decrease of the population over time. Now, we can determine whether this is increasing or decreasing based on our B value. Remember, if B is above 1, it's a growth. If it's between 0 and 1, it's a decay. In this case, this would be a growth problem. So we know that the population here is growing. This is a growth problem. To figure out the percentage of growth, what we need to do is, if it's a growth problem, what we're going to do is we're going to take the percentage, or this number right here, the B value, 1.052. 100% of the original amount as a decimal would be 1. So what we need to think of this as is a percentage, okay? So if 1 is 100%, I'm going to get rid of that 100% and see what I've got left over. 1.052 minus 1 gives me the 0.052. So this represents my percentage of growth. That's how much over the 100% population I have. And if I rewrite this as a percentage, remember, to rewrite something as a percentage, you move the decimal to the right 2 places. So this population is growing at 5.2%. Here I have a couple more examples. In this one, my initial population is 1,500. My growth rate is 0.92. Now this one we know is a decay problem. It's not above 1, it is between 0 and 1, so we know it's a decay problem. In the event of a decay problem, what we're going to do is we're going to subtract my percentage or my decimal from 1. So if it's a decay, we subtract that percentage from 1. If I do that, I end up with 0.08. And then we're going to take that decimal and convert it to a percentage. So this one is decreasing at a rate of 8%. For this one, my initial population is 700, and this is the rate of growth or decay. In this case, it is a decay because it's between 0 and 1. So think about that. You're going to take it, you're going to subtract it from 1. When I subtract 0.724 from 1, I end up with a 0.276. And you can do this on the calculator. You don't have to do it by hand. If that is a decay problem, as we said, then this is decreasing at a rate, if I move the decimal 2 places, 27.6%. So it's a decrease of 27.6%.
So looking at a couple of word problems. This one says in 1983 there were 102,000 farms in Minnesota. By 1998 this number had dropped to 80,000. Write an exponential function that could be used to model the farm population of Minnesota. Write the function in terms of the number of years since 1983. Use the model to predict how many farms would expect to be left in Minnesota in 2003. This problem begins in 1983. And in 1983, there were 102 farms in Minnesota. So if you think about that, time equals 0 is in 1983. And at time 0, we had 102,000 farms. So that really gives us an ordered pair, 0, 102, 102,000. So this, the 102,000, is our initial population. Now we learned that the exponential function is y equals a times b to the x. We also learned that a is our y-intercept, or our initial population. So that 102,000 in my equation will go in for a. So right now we know that at time 0, our initial population was 102,000. And so we have that times b to the x. Then they go on to say, by 1998, the number had dropped to 80,000. So if I just let t, or x in this case, represent the amount of time that has passed in years, and I let y equal the number of farms. Well, if you think about that in terms of y equals a b to the x, well, when time is 0, if I put a 0 right here, wouldn't this whole thing cancel to 1 and then give us y equals 102,000? That's why this is the initial population. That's why we can go ahead and put a in as 102,000. We know that by 1998, in other words, 5 years after the starting point, so at year 5, the number of farms has dropped by 80,000. So if we subtract 80,000 from 102,000, we would end up with 22,000 farms left. Then it goes on to say to write an exponential equation that can be used to model that farm population, and then write the function in terms of the number of years since 1983. Okay, that's what we're working on right here. And it says use the model to predict how many farms would you expect to be left in Minnesota in 2003. Well, in 2003, if we started in 1983, wouldn't that be year 20? So when x is 20, they want us to figure out how many farms are left. That's what we're trying to find. Well, in order to do that, we can put this one into this equation to figure out what b is. So if I do that, y, the total number of farms, 22,000, equals the original number of farms, 102,000, times b. We don't know what the exponential base is, but we do know that x, the number of years, is 5 when we have 22,000 farms. So at this point, I would use my calculator to solve that for b. Let's go to Desmos. Okay, so here I am in Desmos. I'm going to do that math. I'm going to put in 22,000 divided by 102,000. 22,000 divided by 102,000. When I do that, I get 0.215686, and it keeps going. So now I want the fifth root of that number. So if I go down here Okay, so what I want is the fifth root of this number. So I'm going to go down here to my keyboard. And I need to go, notice you don't have the nth root. You have a square root. You don't have the nth root of a number. So I'm going to go over here to functions. I'm going to go to miscellaneous. And see here I have the nth root. I want the fifth root of this number right here. So in this fifth root, I'm going to need to put this number. So I'm going to put that in parentheses underneath my fifth root radical. So 22,000 over 102,000. Get outside there. I'm going to end the parentheses. And that gives me 0.7358. So Desmos, it doesn't really make this easier by any means, but at least we can get a number. So you would write that down on your, now, if you have a calculator at home that does this, certainly, and it's easier for you, go ahead and use it. But you need to understand that on the SOL, if you have to take that test, then you would have to use Desmos. They're not allowing handheld calculators anymore. You're going to need to know how to represent these numbers in Desmos just to be safe. So we know that B from Desmos is equal to and I'm going to go 4 decimal places, 0.7358. Now, usually with something like this, they're asking you to predict what's going to happen or predict how many will be left at a certain time. This is just going to help you with the equation so that you can eventually get your answer. So if this is your B value, that means your final equation for this is y equals our initial population, 102,000, times B, which is 0.7358, to the x being the number of years. So what have they asked us to predict? They want you to use the model, this is the model, to predict how many farms would be expected to be left in Minnesota in 2003. Well, in 2003, remember we said this is year 20. So year 20, we want to figure out what y is. So we're going to put a 20 here in x. So y equals 102,000 times 0.7358 to the 20th power. So I'm going to go back to Desmos and I'm going to put that in there. So we've got 102,000 times, we had the 0.73358 in parentheses, and that is to the 20th power. Gives us 220.6967. Now we're predicting the number of farms in Minnesota. So the number of farms after year 20, if this pattern continues, so that would be in 2003, would be 220 farms, and we would round to the nearest farm, so 221 farms. So my answer here would be 221 farms as my prediction of how many farms are left. So you can make some predictions about real life. Is this a good pattern? Would it be good if there were only 221 farms in 2003 if there were 102,000 farms in 1983? I would say probably no. The United States depends on those farms to produce food. So if it's in the decline this much, that is dangerous to the American people. So we would need to find a way to change this trend so that the number of farms increases. In the next problem, the initial number of bacteria in a culture is 12,000. The culture doubles every day. Write an exponential function to model the population y of bacteria after x days. So y is the number of bacteria at a certain time, x is the number of days. Y is the amount of bacteria, x is the number of days. Giving us the equation, again, y equals a, b to the x. And remember, a is our initial population. So our initial number of bacteria in the culture is 12,000. So where do I put that? Hopefully you're thinking you put it for a. So y equals 12,000 times b to the x. The culture doubles each day. Write an exponential function to model the population y of bacteria after x days. Well, if the bacteria doubles each day, then don't we know that in day 2, we're going to have twice as many bacteria, 24,000? So if this is how many bacteria we know we're going to have the second day, I could plug this in to figure out what B is. See, if we're trying to find an exponential model, we have to know what A and B are to get our exponential model. So I'm going to plug this information in. Y is 24,000. That equals 12,000 times B to the X, and X is 2. At 2 days, we have 24,000. I'm going to divide that over. So 24,000 divided by 12,000. Hopefully you can do that without a calculator. That's 2. 2 equals B squared. So if I take the square root, I'm going to have the plus minus square root of 2 equals B. Our B has to be positive. So if we're just writing the function, that would be y equals 12,000 and B is the square root of 2 to the x. That would be our function.